Good afternoon, bon après-midi. Welcome to this edition of the Physical Society Colloquium. I'm coming to you live from the brutalist majesty of the Rutherford Physics Building at McGill University in beautiful downtown Montreal with its iridescent snowball Earth-like glow. If you are in the Zoom session and you prefer not to be recorded or live streamed, please log out of Zoom and join us via YouTube. This afternoon, we will have a 45-minute talk followed by 15 minutes of questions and answers. To ask a question in Zoom, please use the raise hand feature following the talk. To ask a question in YouTube, please enter it into the chat. The questions will be relayed to me by my sidekick following the talk. After the Q&A session, the live stream and recording will stop. Professors will be asked to log out of the Zoom session, and undergrads, grads, and postdocs, as well as other non-faculty in the Zoom session, will be invited to the après colloque, a chance to get to know the speaker in a more intimate setting. With that, I will now pass to Professor Sean Lovejoy to introduce the speaker. Sean.
So, good afternoon, everybody. It's really with great pleasure that I'm introducing this friend and colleague of mine, Valerio Lucarini. It's actually been 15 years since I first met Valerio. And at that point, he was just finishing his PhD at the University of Joensuu, Finland. And he already had a job lined up at the University of Bologna. In 2009, he moved to the UK, became a lecturer in mathematics and meteorology at the University of Reading. In 2011, he became professor of theoretical meteorology and vice director of the Meteorological Institute at the University of Hamburg in Germany. And since 2017, he's gone back to Reading, but this time as professor at the Department of Mathematics and Statistics. And he's also affiliated with the UK Centre for Earth System Research and Sustainability. So Valerio has won numerous awards. I'm not going to read them all, but recently there was the 2018 Whitehead Prize in Mathematics, and just last year, the Lewis Fry Richardson Medal of the European Geosciences Union. Throughout his career, he has focused his research on applying dynamical systems theory to the earth sciences, and we'll soon find out a lot more about that. And he tells me that beyond physics, he notably participated in an educational project dedicated to inmates in a high security prison in Italy. And he told me over a beer all kinds of stories about that at one point, but also he did theater, and he adds lots of political activism. Yes, I was a member of one of those Antifa groups, unquote. And he mentions that he has a 2-year-old son who keeps him very, very busy day and night, as he insists. Anyway, thank you. Take it away, Valerio.
Thanks, Sean, for the kind introduction, and thanks everyone for the invitation. And it's, of course, a great honor for me to be here, and it's a lot of fun. Actually, I put my son to sleep, quote unquote. Let's hope he stays in that status, but we're not sure. He might jump in, and he will talk a lot if he jumps in, and there's no way to stop him. He has taken from his dad, I'm afraid. So yes, today I will talk about some quite extensive work that I've done with various colleagues. Some of them are mentioned in this first slide. And the idea is to try to have a better understanding of the global stability properties of the Earth's climate. And the work I will present combines different, let's say, viewpoints and different disciplinary approaches. The approach of earth sciences, of applied maths and physics, which a bit reflect my background here. So let me start by saying that, I'm taking care since recently in Reading of the Center for the Mathematics of Planet Earth. So this is an interdisciplinary research center, and please visit it. And if you have ideas for collaboration and at the end of the day, we share the same head of state. I am reminded. It's a good opportunity to set, and there will be opportunities of collaboration between Canada and UK. I'm very happy to share anyway project ideas and scientific ideas in general. Not only me, many other colleagues are involved. And so let's start by saying a few words about the climate. So I will, when we talk about the climate, we talk about a system that's complex and complicated because there is many, in fact, an infinity more or less of degrees of freedom, complex in the sense that we have nonlinear interactions between its subsystems, the atmosphere, hydrosphere, cryosphere, biosphere, and land surface, and within each of these subsystems. And the system has features complexity in the sense that, of course, we don't have a closed solution to the problem. And we have a very interesting dynamics coming out of it. So the system, if we want to classify it from a physico-mathematical viewpoint, it's a really good example of a non-equilibrium system, as it is a system which is driven by inhomogeneous absorption of solar radiation. Solar radiation is preferentially absorbed at surface rather than aloft, and preferentially at low latitudes rather than high latitudes. This is why at a certain point, while I was in Hamburg, I decided to spend some time in Goa, India, just to enjoy the extra incoming absorption of solar radiation. Anyway, this dishomogeneity is the main driver of the entirety, is the driver, in fact, of the entirety of interesting phenomena we see inside the Earth system, down to the existence, in fact, of life. And all the motions associated to geophysical flows, as well as radiative exchanges, phase transition, transport phenomena, have to do with this inhomogeneous absorption of solar radiation. So homogeneous words are gray and dull. So indeed, we can see there is a thermodynamic view to understanding the properties of climate that can allow us to create a model, actually a rigorous model of climate as a non-ideal engine, where we can define efficiency, where we can define work and dissipation. And indeed, the very first really relevant scientific contribution of Ed Lorenz, the father of chaos theory, has to do exactly with the construction of the thermodynamic equivalent and the thermodynamic description of the climate. So now I mentioned complexity. And when I say complexity, I think the easiest way to understand this complexity is to look at some sort of semi-quantitative power spectrum of atmospheric observables. So what you see here, it's something that people in earth science like a lot, and it's called the Stommel or Mitchell diagram. And it represents, as I said, in a semi-quantitative way, so you can think it in a logarithmic scale, in some sense, the amount of variability at different spectral frequencies. And whereas the input of energy that I mentioned before enters at very specific frequencies, monthly, annual, because we have seasonal cycle, daily, 1 day to the -1, daily cycle, sunspots, and other, of course, astronomical forcing on the scale of thousands of years. Here we have variability of the system that extends over an enormous range and gives us a continuum spectrum, which is intimately associated with the chaotic nature of the flows. And somehow, this is a very important problem, and this is the fundamental reason why I strongly believe that understanding the climate, the dynamics of climate, is one of the most difficult problems in science today. There is no time scale separation between the different phenomena, okay? And whereas most of the powerful mathematical theories we have and that we use regularly to construct mesoscopic theory of physical and chemical systems rely on the assumption of time scale separation. So in this sense, the climate is an extremely difficult problem to study. And if we look at time series of, in this case, proxy for temperature, we see indeed that the system has variability on very different time scales, and there are huge fluctuations in the course of the history. And something I want to say is that because of the non-equilibrium nature it is extremely non-trivial to relate the natural variability of the system to its response to forcing. So in near equilibrium system, we have that magic tool, the fluctuation dissipation theorem, that under very general hypothesis allow us to translate a natural fluctuation variability into response. This is actually how we have really learned everything we know about materials in particular. In a non-equilibrium system, this is not the case, okay? And that's why it's the understanding, this is another reason why understanding the properties of the climate system is a great challenge. And understanding the relationship between climate variability and climate response to forcing is intimately related to three major problems of contemporary science. Of course, one is the anthropogenic climate change, but we can be a bit more, in some sense, ambitious. The interplay between the evolution of climate on the paleo timescales and the emergence of life. And if we are even more ambitious, the understanding on the fundamental properties of habitability in exoplanets. Okay? By the way, the most recent Nobel Prize was given to those who discovered exoplanets. So the other interesting, another interesting aspect of the dynamics of climate is that if we look at the first response of the system to perturbations, we have all regimes of response. So we have a smooth regime, we have some sort of regime where we have a very strong dependence of the properties on the forcing, and we have critical transitions, which are called in Earth system literature tipping points. So somehow we have a macro system for which some of the ideas that are typical of physics still apply, but need in fact to be strongly generalized. Now, when you talk about climate change, usually when you hear about climate change, you're shown a figure like this one. So there is this figure where with increasing CO2, there is a trend with, of course, noise of increasing globally average surface temperature. So I call this the boring picture of climate change. Also, it gives a fake sense of control in the sense that, you have CO2 going up, temperature slowly piling up. Everything looks in some sense trivial, controllable, okay? But this is not actually the essence, the true essence of climate change. There is much more. When you talk about climate change, there are risks associated to crossing the so-called tipping points associated to the tipping elements. So there are some aspects, some subsystem of the climate system for which changing the atmospheric concentration, changing the CO2 concentration and the ensuing change of climate leads to catastrophic / very rapid / very intense qualitative even changes in the properties of the system. So just to mention a couple of examples which are very relevant. So of course, one of the possible impacts of climate change on decadal timescales is the dieback of the Amazon forest that could become a savanna. Another possible very serious impact could be the transition to an erratic regime of the Indian monsoon, with the ensuing effect you can imagine on the livelihood of about 1 billion people, and another important example is the possibility of meltdown of the permafrost, which is something that indeed we are observing, and you see it in the news now and then. These tipping points can be dynamically linked, and this is the so-called domino effect. Now, I want to show you a last time series. And this is a time series that telescopes itself from the last 5 million years up to the last few tens of thousand years. So what you see is that this is in the Quaternary, we have glaciations. And as you can see, if we focus ourselves in the last 500,000 years, we have on and off states of ice ages. And if we look inside one of these ice age, we see inside the ice age on and off states. So there is some sort of hierarchy in the transition. So inside what I would call macroscopic states, there are possible competing, smaller scale competing states. So it's it's a system which has, in some sense, a hierarchy, and I will try to make this more concrete at the very end of this presentation. Just keep this in mind for the moment. So, if you want to know more about the relationship between forced and free variability in climate, I strongly recommend you to give a look at this recent review paper I wrote with Michael Gill on Reviews of Modern Physics, where we describe this in detail. Now, as I said, there are different regimes of climatic response. So I will focus only on the last part, but just to mention, we have a smooth regime of response, which is actually closer to what somehow it's, what we are observing now. And in some sense, it is possible to do climate projections with high accuracy by constructing response operators that are at formal level not very different from those you study in standard statistical mechanical systems. So you can use some extension of the so-called Kubo theory you study at the university, and you can use this to predict the climate change. So this allows you to learn about the local properties in some sort of parametric space of the climate system. Then when you get close to the so-called tipping points, you observe what is called the critical slowing down. So I will not go here in the maths because this is not what I will talk about today. But let's say you are in a regime, you can create a mathematical formalism to understand the fundamental concept that near a critical transition, the negative feedbacks fail to do their job, and so you are victim of the positive feedback, the feedbacks that kick you from one mode of operation to another mode of operation. And now we go to the topic of today's presentation, that is the regime of critical transition. So in a system that is multistable, and as I will explain you in a moment, that more specifically that the climate is such, it's extremely important to understand, study such a multistability and understand the mechanism, mathematical and physical, through which we can perform transitions from one state to the other. And in particular, noise will play a major role here. And in so doing, we are able to explore the global stability properties of the systems. So now, when we face a critical transition, we go through a phase where it's not clear what's going to be the end. So my main inspiration for understanding critical transition is not the final outcome, which sometimes it's pretty obvious, but is what separates one outcome from the other. So let's be more specific. When we talk about today's planet, we live in something like the top right corner. And I will call this the warm state, whereby I mean a state where we don't have a global ice cover. But if you want to play dice with some evil divinity, you choose which one you prefer. Indeed, but today the planet Earth could be in a different state. That is the snowball state. By snowball, I mean a state where the globally average surface temperature would be of the order of minus 50 Celsius, 2020 Kelvin, and there would be global ice cover and very small temperature difference between equator and pole. So the second state is compatible with the astronomical and astrophysical boundary condition of the planet and with its physical-chemical composition. And indeed, we have been in that state about 600 million years ago. And guess what? We've been flipping in and out between these two states about 600 million years ago. And guess what? The multicellular life started to appear just after the last time we flipped into the warm state where we still, fortunately, are. Now, let's first see on simple physical arguments why such multistability, which came to a shock, is possible. So we have a competition between two feedbacks, a negative feedback, the Boltzmann feedback, which basically says that the warmer a body, the more radiation it emits to space in this case. And the second one is the ice albedo feedback. A colder planet where water is available, this is implicit, will have a higher part of its surface covered by ice. The fact that there is more ice means that more radiation is reflected to space. So you immediately see that this creates a positive feedback. So now there is a simple way to model the albedo, which is a function which is about 0.2 in the case of warmer temperature. Think about the ocean. The ocean is dark, so almost no radiation is scattered back to space. And instead, if the temperature is low and we assume there is ice cover, alpha is very large because, of course, snow and ice reflect very well the radiation to space. So you write this energy balance model, zero-dimensional energy balance model. You put in some sort of macroscopic parameters which are typical for the Earth, and you get that there is a range of values of the incoming solar irradiance where multiple states are possible, a warm state and a cold state. The cold state is usually called the snowball state. And the tipping point is exactly the point where the bifurcation takes place, where one of the two states loses stability. How does it lose stability in this class of system? Through the mechanism of a basin boundary crisis. Boundary crisis, that is, the stable state shakes hands with an unstable solution which sits in between and which corresponds to the local maximum in the potential describing the dynamics of the system, and the stable point and the stable point shift, and both disappear and only one solution appears. So it remains. So in this case, for stronger solar, very strong solar irradiance, incoming solar radiation flux, only the warm state is possible. For for very weak incoming solar radiation, only the cold state is possible. But for a very substantial range of values of the incoming solar radiation, and our planet nowadays is more or less in the middle of this, we have two competing states. Now, with a former student of mine, Robert Boschi, did this analysis with a full climate model. So this it's a full climate model, but not what I would call a state of the art. So it's a model which is only, so to say, 10 to the 5 degrees of freedom instead of 10 to the 8 degrees of freedom as the state of the art models. Still, it has an atmosphere, an approximate ocean, biosphere, clouds, whatever you want, and he has been able to reproduce the bifurcation diagram of the planet Earth with respect to the control parameters given by the solar irradiance and CO2 radiation. So now, sorry, made some mess. The question is, let's say we are in the region of bistability. So we have one stable solution, which will be the warm climate, which of course is not a fixed point. This will correspond to a system living in a strange attractor with very complex dynamics. Then we will have, at the same time, a competing solution, which is instead a snowball state, which I can tell you, without going into detail, will have a much weaker dynamic. Still, it will be definitely a non-trivial world. The question is, what lies in between the two? Is there an in-between? Is there something real sitting between these two states? So to understand this, we have to go to some mathematical literature of the 80s, mostly due to Grebogi, Ott, and York. And they proposed some sort of fundamental mathematical framework for studying multistable systems. So systems where there are multiple competing attractors. So say you have an attractor omega 1, a second attractor omega 2, and correspondingly two basins of attraction, so that your asymptotic states depends on your initial condition. And then the question is, there must be a boundary between these two basins. And what is the dynamics of an orbit initialized in the basin boundary? So what you have is that typically Inside the basin boundary, there is what is called a relative attractor. So if you start in the basin boundary, you're going to be attracted by it. If you're just nearby the basin boundary, of course, you will be repelled to either attractor, but for a while, you will be close to such what is called saddle edge state. So this edge state is, in some sense, what separates the two attractors. And this edge state is the place where, if I add noise in the system, I anticipate it now, the transitions will take place. So noise-induced transitions go through such an edge state. So this edge state is like a mountain pass. Okay, so this is the idea we have to keep in mind. And now, this is the beauty of earth sciences. You go from this grayish picture to pictures with colors. So we have the snowball state, which is blue, of course, the warm state, which is red, and the edge state is green. And we call it melancholia state, and we make it green because, for a reason it will become apparent. So when you study multistable system, very often the sort of the temptation is to study either state. So as an example, I want to study the warm state, I want to study the cold state, and if I want to create some sort of cinematographical narrative that is of interest, I study how state B goes into state A, and the movie The Day After Tomorrow is this. And instead, you can focus on state C, on the melancholia state, and it's called melancholia state, not by chance, because the idea of studying this class of problem came to me while watching the movie by Lars von Trier, Melancholia, which was released in 2011. And by a bizarre twist of fate, 7 years later, I had the chance to present the movie at Barbican in London, which is sort of very cool place. And I've had the chance to talk to that audience of the problem I'm also discussing today, which was fun. So what we did here is that we wanted to appreciate the multistability of the Earth. We wanted to understand the properties of this system, but not taking a very simple model. We wanted to be, I wouldn't call it realistic. I don't know even what realistic means in some sense. I wanted to be able to appreciate the complexity and the presence of variability on many scales for my system. So we started by creating a simple climate model, which has still an atmosphere which has turbulence. So there are cyclones, there are blocking events, and so on. And we have dissipation, we have a very highly chaotic dynamics coupled to a simple ocean model. And the idea was first to construct this melancholia state. So remember, this melancholia state sits in the basin boundary. So it's impossible to find it through direct numerical integration. What you have to do is to use a method which is called edge tracking, by which, by bisection, you construct this state. And so somehow you are able to live in this, what I would think as a blade, in this ridge, which is the basin boundary, and ride the ridge until you end up in this melancholia state. And you can prove that this state is real. It's a very real solution to the problem, but unfortunately, it's unstable. Okay? And when you look at this problem, you start to see some interesting mathematical subtleties. As an example, that in many cases, the basin boundary between the two states is not a manifold, but is a fractal set. And at all practical purposes, this means that when you are in this regime, when you have two competing states which are chaotic and you are in high-dimensional chaos, things are never easy. They are complex because the boundary separating the two, as I said, is not a manifold, it's a fractal set. So there is like a gray region where where you basically, by moving a little bit your initial condition, you are at risk of falling down into either solution. So you don't have what is called the predictability of the second kind, according to Lorentz. So there is this sort of beautiful emergence of complex geometrical properties that come from this complexity. And one thing we managed to do with my collaborator Tamas Bodaj was to construct a phase diagram of the climate, whereby you have the warm state, you have the cold state, and actually there is much more, but in particular, you are able to find this melancholia state I was mentioning you. And guess what? When you start to look carefully enough, you start to discover there is more than two states. There is, in fact, also in some parametric regime, a third hidden pathological climate state, which starts to tell you that maybe the climate is a more complex object than just what we live in, and there is more than this. As we said, there is the snowball state, and maybe there is more, and we will see later that there is even more. So somehow we start to have the idea that there is a multiplicity. I mean, the climate is in some sense a multiverse. There are many competing climates that live in parallel, in some sense. We live experiencing one, but there are other competing states where we could have been. And I leave you the thought of what this implies in terms of habitability when we think about billions of exoplanets around the universe. Okay, now let's go back to something a bit more concrete. So when you have these competing metastable states and the dynamics is deterministic, there is no way to perform transitions from one state to the other. But instead, if you have noise, as I mentioned you can perform transition. And the problem of noise-induced escapes from attractor is a very classic problem in physics and in chemistry. That's how basically many reactions take place. So there are ways to formalize the problem of noise-induced escapes from attractor also for a complex system like the climate. And this goes through introducing an energy-like functional, which is called quasipotential, that somehow it's a scalar field that tells you about the stability properties of the system. In particular, you have that the local minima of this quasipotential are associated with attractors, and the saddles of this potential are associated with this melancholia state. So you have a technical characterization of the system to a scalar field. Okay, so now you have to think a climate in some high-dimensional representation as something like this picture, where there are many, where the field phi has various local minima. Each local minima corresponds to a different climate, and noise allows us to perform transitions between these. So this is the sort of mathematical model we have in mind. And indeed, there's been a growing body of literature that shows that one can find up to several possible competing climates. Very recently, a group from Geneva published a paper where they showed on an actually fairly reasonable global circulation model, which includes also the ocean, so it also allows for dealing with longer timescales than we did. They find 5 competing climate states. So we see that there is so much complexity about the climate that we are just starting to learn. And one can start to see that the ultra-long scale variability of climate might just, so to say, be an itinerancy between such many competing states. Who knows? Okay, anyway, I want to say that what one could say, what could see indeed, and I will skim through some of the results to give you the qualitative features rather than quantitative one, is that indeed one can prove that there are these competing metastable states, and the melancholia state that I mentioned before is indeed the gate for noise-induced transition. So you can really sort of explore this high-dimensional geometry of the system, even in such high-dimensional model. And look that we have not used any ultra-fancy high-performance computing. We use a regular cluster. So somehow the idea is we can approach the problem of climate using rigorous maths and physics, still keeping a high level of complexity, without the need to be the close relatives of Bill Gates, okay? Now, the transitions take place through the so-called instantons. So these are special paths that minimize a functional. So they solve a variational problem. And so in some sense, they are the most classical object you can think in physics. And this minimal cost means that in the weak noise limit, this is how transitions take place. So this is the sort of, sorry. So somehow this is the nice link with classical approach in physics. You construct an action, you minimize the action, and this is how, in the weak noise limit, you're gonna go from one metastable state to another metastable state. Let me say this again to connect to other aspects of physics. So let's look again at how these invariant measures, so the probability of being in a region of the phase space of the system, looks like. So you see here that apart from the pre-exponential factor z of x, w is this measure, so it's something that is normalized to 1, and x is a very high-dimensional vector, it is written in what is called in a large deviation law form. That is, you have the exponent of a function, of a rate function, that would be phi divided by times 2 over sigma squared, where sigma measures the intensity of the noise. So you understand that when the noise becomes very, very weak, this function concentrates in the regions where phi is very small, because all the other regions will be exponentially penalized. So what we see is that if we have a system with various local minima, they correspond, as I said, to multiple competing metastable states. But when I approach the problem from the stochastic point of view, and then I send the noise to 0, my measure will not see anymore all of these attractors, but will only see the attractor with the lowest value of the pseudo-potential, quasi-potential phi. So the zero noise limit will select one special solution. So this is a case where the stochastic and the deterministic viewpoint give us different pieces of information. So now, just to give you an example, this is the bifurcation diagram I showed you before. And let's just focus on the dichotomy between the red line, the green, and the blue line. So warm and snowball state, and the green state is the melancholic state in between. So now what happens that if I run my model forward in time with some noise, I will jump between the two states. But if the noise is very weak, what will happen? That my system will basically persist overwhelmingly over one of the two states for the reason I mentioned before. So in particular, for mu, which is the relative solar irradiance, so it's 1 for present day irradiance, is larger than 1 if you assume the sun is stronger, and is smaller than 1 if you assume that the sun is weaker than today. So if mu is smallish, then even if the system performs fluctuations between the warm and the cold state, it will stay predominantly in the cold state. And if we further decrease the intensity of the noise, it will freeze, since the system will freeze, and now I'm talking in sense of Metropolis algorithm, the system will predominantly only, will basically never leave the cold state. And similarly, if mu is large enough, the selected state will be the warm state. So in some sense, we observe a phase transition in my system. So if we send the noise to 0, what in the deterministic case is a multistability will become de facto instead the multistability will be lost, because for lower values of mu only the cold state will be populated, and for high values of mu only the warm state will be populated. And you can think this exactly as in terms of the classical thermodynamic phase transition you have studied. So you see a very similar effect for which you have an interpretation, okay? So instead of looking at the free energy of the system, you look here at this quasi-potential. Now let me come to the conclusion, to the just very final results. So up to now, we have been playing with, let's say, simplified climate models, not with something that really has all the complexity we would like. So now we went from using this atmospheric model with some simple ocean model. We try to investigate again, using these ideas of statistical mechanics, the climate, the dichotomy between warm and snowball state, using PLASM, which is a model I mentioned before, but it's as I said, it's the model my student Boschi used and that I mentioned before. So it is a model that has all a description of all the main components of the climate system. And in particular, it has a hydrological cycle, it has, as you see, vegetation and so on. So now, this model performs transitions. And I will show you how this, so top left is the transition snowball to warm, and bottom right is a transition from warm to snowball. So on the 2D diagram, you see the black line which describes the transition, and the red line is, in the case of snowball to warm, the stochastically averaged transition, which is basically the instanton, and the same in the lower panel is blue. So the thing you see is that the forward and backward trajectories are not the same. So you see that the red line does not at all look like the blue line. So that means that the process of going from glaciated state to deglaciated state is different, fundamentally different from the process of going from a deglaciated to a glaciated state. These are transitions due to fluctuations in the incoming solar radiation. So these are noise-induced transitions. So the existence of this difference between the two paths is a fundamental manifestation of the non-equilibrium nature of the system. So in some sense, we see deep statistical mechanical properties just by looking at this in the quantities. So this is in some sense a proof of rigorous proof of non-equilibrium. So, and not only this, we are able to see that in a system like this, the things become always more complicated than in the idealized case. So we don't have only one saddle that allows for transition between snowball and warm. There are two saddles. So when you go from snowball to warm, you cross the basin boundary in a place, and when you go from warm to snowball, you cross the basin boundary in a separate location. So again, this makes, in some sense, the system much more complex than before. And we analyzed two setups. The setup I just described is the setup where the ocean is allowed to perform meridional heat transport, and then we studied a separate setup where the ocean does not transport energy from the equator to pole. It just permits vertical exchanges of energy and momentum, of course, and water mass with above atmosphere. So this system has a different climate, but the amazing thing is that now by using the so-called swamp ocean approximation, which is the one I described, we still have, of course, the warm state. We still have the snowball state, which is on the right and on the left of this panel. And then, miraculously, in some sense, a third stable climate appears. A third stable climate where the ocean, the Earth is almost entirely frozen, except a small band near the equator. And this special climate had been studied and proposed as very relevant, in fact, for the reason why life survived in our planet during the snowball events that I described before. So maybe we didn't really go 600 million years ago through a snowball state. We went through what I call here a cold state, okay? A water belt solution. And I will not go into detail. I will just tell you that here things become much more complex. Sometimes the transition between cold and snowball are direct. Sometimes they are mediated through the cold state. So the cold state attracts. It's a true solution of the problem. It has a non-vanishing basin boundary, so it does attract a solution. It's a true climate. It is just a weakly stable climate, but it is a stable climate. So I may come. Now, how have we discovered this sea state? And the answer is by sheer luck, because the basin boundary of this sea state is very small. And we basically discovered it because we were just playing a bit in the region between that was we knew was separating the basin of attraction of the warm and the snowball state. And somehow running, we found this strange solution, and then we realized actually it was very real. Sometimes you have to be lucky in your investigation, and we have been very lucky. So, but sometimes this serendipity is a bit scary. So we decided to reapproach the problem, because sometimes it's good to look at the problem in a different, through different methodologies with different eyes. So we said the following: why don't we instead run a very long simulation with stochastic noise? So the system goes everywhere in the phase space, and then we use some methodologies of data, of machine learning and of data science that allows somehow to automatically construct clusters of solutions. So we did this in collaboration with a colleague from CISA Trieste, who is a wizard in this. And we just gave him, in a sort of double, in a blind, without telling him anything about the system, without telling him what we had found, this data from a long integration. And he actually chose only a subset of the data, because you have to think we had about 10,000 years runs, and the system has 10 to the 4th and to the 5 degrees of freedom, and we have, say, 1 datum per day. This is an enormous amount of data. So instead, you can take some sort of a very heavily projected version of the data. So it's, instead of a vector with 10 to the 4 elements, you take just 50 or 100. You feed in this magic algorithm, and what was possible was to reconstruct these, the 3 competing states, and to reconstruct also the properties of the corresponding attractors. So somehow the bottom-up approach confirmed and allowed to rediscover what we had found by luck somehow. And these methodologies, which are just starting to explore, allow us really to, I repeat, we found states A, B, and C by direct numerical integration without noise. And remember, if you use numerical integration without noise, you cannot, this final solution will depend all in your initial condition. So you might well miss some solutions because you don't start simulations from the right regions of the phase space. The power of this methodology here is that you don't need you go straight through the stochastic approach that allows you a global exploration of the phase space. So I think that this has a huge potential for studying not only climate model outputs, but actual observational data. And this is something we are doing now. So now the final statement was, and connecting again to physics, was this. You might remember that I said that in the first model, which is on the right-hand side here, we had 1 melancholia state. And in the second model, setup A, where we only had 2 states, we had 2 melancholia states. And the fact that we had 2 melancholia states made it possible for us to have macroscopic currents. And to have macroscopic currents means that the system is very, very clearly out of equilibrium. So what is the reason for such difference between these two? Is there a way to interpret physically this difference? And the result is that indeed the difference is the following. In the second model, model 2 plasm, we have, as I said, the hydrological cycle. So we have water doing all of its job, changing phases, being transported, and through the phase changes, basically absorbing or emitting the enormous amount of energy. And remember, water has an enormous relevance for today's climate, whereas the first model is a sort of a much more idealized model where there is no water. In other terms, the result is the following. The presence of water is an essential ingredient in the irreversibility of the planet. Stronger irreversibility is an indication of more out of equilibrium conditions. So in some sense, there is a relationship between this more complex geometry of the phase space and the very physical property that a climate with water has higher entropy production, which is somehow what we found. Concluding, this is the dichotomy because snowball and warm state. But as I said, we see this multistability at different hierarchical level. So very different, warm and snowball, and then inside each glacial cycle, there are the relatively warm and the relatively cold phases. So, and nowadays, we have multistability on smaller scale associated with these tipping elements that I mentioned you. So what I propose is the idea is that when we look at the planet, we have multistability, but we have multistability on multiple scales. So going to Richardson, he said, he had this sort of almost, it's a limerick almost, to said, saying that, you know, in order to describe turbulence, which says big walls have little walls that feed on their velocity, and little walls have lesser walls, and so on, to viscosity, to describe the turbulent cascade in turbulent flows. And now, in some sense, we can embarrassingly do a paraphrasis of this and think that if we look at the Earth system, we have very deep metastable states, and inside these deep metastable states, there are shallower metastable states, and so on. And so there is a hierarchy I see. My idea is that what I'm seeing now, the global phase properties of the climate as characterized by the presence of multistability, and each stable state in itself as on smaller scales is decorated, so the quasipotential is decorated by shallower minima on smaller scales. And somehow, by noise, we explore this complex landscape, and depending on the intensity of the noise, we wash out some features. We can appreciate others, but if the noise is too weak, it's impossible for us to explore the large-scale features of this landscape. So, conclude here, and I leave this last slide for you to read. Thank you very much.
Oh, thank you very much for a fascinating presentation. So if you enjoyed the presentation, please say so. If you're in the Zoom session, write something in the chat. I can share the chat transcript with Professor Lucarini at the end of the talk. If you're watching on YouTube, please go ahead and write something in the YouTube chat about how much you enjoyed the talk. This is the time for questions. So we have still, you know, a good 9 minutes for questions, and there have been a couple that have come in already, one through Zoom and one through YouTube. But yes, if you would like to ask a question and you're in the Zoom session, please use the raise hand feature. That'll bring your name up to the top, and then I can pick you off one by one. And if you want to ask a question and you're watching on YouTube, please go ahead and enter it into the chat, and it will be passed to me, and I'll ask it out loud. Okay, so with that, I will ask the first question, which comes from YouTube. The first question is, in the plot you showed with ice volume and temperature, it looks like the warm periods are typically shorter than the snowball periods. Is there a deep reason for this?
Sorry, can you repeat? I couldn't hear very well. Deep?
Yeah, in the plot you showed with ice volume and temperature, so there was a plot, I think, that one that you flashed by just a moment ago. You passed, it came up twice, once at the beginning and once at the end. So you have there it is, on the ice temperature changes. It looks like the warm periods are typically shorter than the snowball periods. Is there a deep reason for this?
Okay, yeah, these are not really the. This is on the scale of ice ages. That's not So when we talk about ice ages, as one can see here, we are talking about changes of temperature of 5 to say top 8 degrees on a global scale. To give you a sense, so this is the ice age we know, you know, the Neanderthals and so on, the mammoths and all the cool stuff that some people are trying to resurrect, by the way. And when we talk about snowball versus warm, we're talking about temperature differences which are 1 order of magnitude larger, so about 50, 70 degrees difference. So anyway, also in this case, there is an asymmetry. Because, as I said, and I mean, this actually is a good point to take when we will be our paper will be butchered by reviewers. Is that it's another manifestation that the process of melting and of glaciation are very different. They're not one the opposite of each other, okay? So it's well known that the cycle is asymmetric. And somehow what we have shown, looking in that case at the snowball versus worm case and the transition between the two, is a sort of a statistical mechanical appreciation of that. Okay.
Okay, thank you. There's a question from Zoom, from the Zoom chat. Do we know that there is no other attractor basin with a higher temperature than the warm state we are in now? And then it goes on. Or do we know that we are not in a melancholia state, which is about to fall into a hot basin?
Oh, yeah, this is actually, there is the hothouse Earth. So indeed, if you explore the warmer range of temperatures, and if you consider forcings due to increases in solar radiation or changes in the CO2, there is a difference, but not a fundamental one between the two. There are, it's far from being possible to exclude the existence of a competing warmer state. Indeed, in the publication I mentioned before, here, where they had 5 competing states, this one here, okay. In this publication published last year in 2019 on climate dynamics, they find the 5 competing states, and they have a warm state, which is indeed more or less present day state, and there is a hot state, which is few degrees warmer, where there is no ice, there are no ice caps. So yes, I cannot exclude the fact that even now there might be a competing warmer state, and actually there is ample evidence that we could be in a world with no ice. Historically, of course, the planet for most of its existence has been iceless. I mean, in the sense of, except in high mountains. Okay, we have permanent ice on Antarctica and in Greenland since only a few million years. Keep in mind that at the time of the dinosaurs and even later in the Eemian, we had much warmer conditions from now, and not just things were warmer at the equator. They were much, much warmer at high latitudes. So I believe it's very thinkable, the existence of what called the hothouse solution, and going towards higher temperature makes the transition to that state more likely or more possible. This is the understanding of this is goes into the lingo of the so-called safe operating spaces. So which are the paths of change in the properties of our climate? And here I'm thinking mostly about land use and CO2 concentration and so on, that make such a transition towards a potentially dangerous, qualitatively different climate state, with no permanent ice or much reduced permanent ice possible.
Okay, thanks. There's another question from Professor Sean Lovejoy. Sean, could you please unmute and ask your question?
So thank you very much, Valerio. At the end, you mentioned cascades, and these are scaling. How does scaling fit into all of this in the end? I mean, you had some beautiful fractal image and whatnot, and you had Richardson's poem, etc. But how do you?
It's in that sense. It's I'm not sure you have self-similarity, okay, but I believe you have some sort of a hierarchy in that sense. So let's go back to the left panel here. So in the left panel, I have, let's take where the coarse grain graph 1, okay? So this tells you the quasipotential in some sorts of, large scale. So assume that the left-hand side is the cold snowball state, and the warm minimum, and the minimum on the right-hand side is the warm minimum. So say we are in state 1 at this level, okay? We are definitely not in a snowball. So then you go into, level 2. So you see that inside state 1, there are actually smaller, some undulations in this minimum, if you look more accurately. So, and then in this undulation, there are competing states. So in particular, there could be a glacial and an interglacial, and we are now in a glacial area. But we are not just in a glacial area, we are in the warm phase of a glacial area. That will be 3, okay? And if you go even deeper, you could discover that we are in the warm scale of an interglacial area of an overall warm period. And not only, we are, as an example, in a regime where the thermohaline circulation is active. But there could be another competing state where the thermohaline circulation is off, even if one would still be in the warm state of an interglacial, of a glacial era inside the warm planet. So the idea is, I believe that we can think not just, so usually the view on tipping points is a geographical view. So I have multistability in the Amazon forest system, okay? Or in the thermohaline circulation or in the Indian monsoon. My proposal is to look at this as a problem of competing scales. That is, where by scale, I mean really the scale of these quasipotential. So you have on the largest scale, sort of vastly separated attractors. But then if you look at one of the two attractors and you look carefully enough, in fact, it's almost broken in more than one pieces, and so on and so forth. So that's the idea. And then I don't claim that there is a self-similarity between this, but I claim that there is a hierarchical structure, okay?
Okay, thanks.
Okay, thank you. Just a reminder to everyone in the audience who is not a tenured or tenure-track professor, you are welcome to stay for the update colloque, which will begin in 5 minutes. But in the next 5 minutes, we have a couple of questions, so I'll take those questions in Zoom. First question comes from Professor Nick Cowan. Could you please unmute and ask your question? Nick, could you please unmute? Nick, you're still muted. I don't know if, okay, if maybe Nick has stepped away or is not able to unmute. We had another question, but I think the hand went up and down from Leo Fomenti. Would you like to unmute and ask your question?
Sure, thanks. What makes your climate analysis different so that it can actually be run on clusters instead of supercomputers?
Oh, no, this is, it's just because we are using a climate model that is, would have been a good climate models of the, say, in the early 90s, okay? So, but it's not a state-of-the-art GCM. So the problem is, and I think this is a more general question when you look at climate modeling. So climate is one of those fields where it is not true, and this is well known since ever, that the most detailed model is the best tool for studying every problem, okay? So the problem is, if you use a very highly, state-of-the-art, say CMIP6 style climate model, this is extremely good to look near the present climate. But for both technological reasons and in the sense of computer cost and formulation of the model itself, this is much less flexible than other models. So somehow the idea is we have to strike a balance between flexibility of the modeling and let's say realism of its representation, and you cannot span both to the extreme. So the nice thing about PLASM, and this is why it's used a lot in various communities, including by astrophysicists, in fact, is that it's flexible enough. It's, let's say, gives you a very, very reasonable climate. It has, if you look at the statistics of a lot of quantities, they are pretty good for the present climate, but is such that you can push it hard, far from the present climate, and still have control on the solution. As an example, checking energy balances or water balances or things like that. So this is why there is nothing magic. It's just that if you want, sometimes making a parsimonious choice helps. Okay, that's my answer. But this opens the door to I think it depends a bit on the background, on the priorities. If you have a certain computer time, would you use it to run a model at the highest possible resolution with the highest number of processes in it, or would you use a much lower resolution model and send maybe hundreds of ensemble runs? I would choose the second without a second thought. But there are also good reasons to choose to follow the first option. Depends a bit on your priorities. I believe that if you want to make a study of processes and some sort be robust in your physical and mathematical statement, you need statistics as much as possible.
Okay, thank you very much.
Yes.
The microphone problem, sorry, was on my end. I forgot to change the setting to allow people to unmute. So Professor Nick Cowan, would you like to ask your question? It'll be the last one of the evening.
All right. So you mentioned exoplanets a few times. And so as someone who actually studies exoplanets, I was trying to think through how to do kind of testable, experiments with this. And it occurs to me that looking at a variety of exoplanets is a little bit different from looking at the Earth over history, because with an exoplanet, because of hysteresis problems in climate, when you look at an exoplanet, you see it as it is today, but you don't know what it was like in the past. So comment on that, or is there anything that you think we could test or learn from studying a variety of diverse exoplanets?
Well, that's again, it's a bit of what are the hypotheses you make. So one thing is, and that's something actually we also studied with that student of mine, Boschi, and similar results have been obtained by Abbott, is that as an example, if you change the rotation rate of an Earth-like system, the range of bistability changes dramatically. So if the rotation rate is faster, and it's clear why in some physical sense, the range of bistability is smaller until it disappears for the 2-to-1 resonance, basically. You get a beautiful picture where that hysteresis graph becomes a vertical flex out of a textbook of physics where you study magnetism. So you get these nice features there. Now, of course, if we have just one snapshot, we see the planet as it is, of course. But I think if we want to assess habitability of some classes of planet, one has to do this parametric study, because of course, you know better than me, you see just one epsilon of what is around there. And so the idea is, I think if we want to consider habitability conditions, we have to assume that they are radically altered the moment you consider multistability, and especially the fact that different astronomical parameter change the quality, not just the quantity of this multistability. So if you change the angle of the axis of rotation, this again changes. You can have a situation that seem like being always way out of the habitability range, and instead you could have life, because as an example, if you are of course in a 1-to-1 phase lock, the substellar point can sustain life even if you are far from the star, because you always have radiation. But that's one case, the most obvious one. But somehow I believe that this multistability should enter the picture of habitability, because consider snowball Earth versus a warm Earth, or even more versus a hot Earth. This is 80 degrees difference. So, these are two planets. If you saw these two planets, how could you even think they could be two sister or two brother planets, how you want to see them? They are, they're as different as Mars and the Earth, more or less. So that, to me, I would say that when we do modeling, and I know, I interacted quite a bit with astrophysicists, of course. In many cases, the priority is looking at the radiative codes. And the quality of the radiative codes of the colleagues in astrophysics is, something absolutely incredible. The problem is sometimes there is less attention on the dynamics. And I understand very well why, because you don't see much of the dynamics from a telescope or from a satellite. But the thing is, the dynamics can change dramatically the budgets, because you can redistribute in ways that are more efficient than radiation, especially if you have phase changes. Because phase change, I mean, I see the presence of the water is a magic substance, because the latent heats are so large that from the point of view of climate, and actually this can be made even more precise if you look at these entropy budgets. I mean, water is a magic substance that takes energy from here and releases it from there. And the entropy production is this energy miraculously transported times 1 over the difference of the inverse temperature. And this is irreversible, okay? But from the energy viewpoint, you have moved this enormous amount of water, of energy from one place to the other. Yeah.
Okay, thank you very much. So thanks once again for joining us for this colloquium. Please, if you would like to thank Professor Lucarini again, and you haven't done so yet, please write something in the Zoom chat. I'll be able to share the chat transcript with him at the end. If you're watching on YouTube, please go ahead and write something in the YouTube chat. And those of you who don't have tenured or tenure track positions, please stick around for the après colloque. Before that, I wanted to make a couple of announcements about the upcoming colloquia. So that concludes this edition of the Physical Society Colloquium. Thanks to all who have joined us. Please join us again next week for a talk by Lisa Manning from Syracuse University entitled Biological Tissues as Mechanical Metamaterials. Following that talk on February 26th, we'll be off YouTube, but we'll have a Zoom-only session for the department. We'll have a presentation of the department climate survey results. So please come for that if you're in from the physics department. The week after that, on Friday, March 5th, we'll have our spring break, so there will be no colloquium. And the week after that, there will be a very special colloquium on March 12th. So mark your calendars for Professor Stefan Alexander. He's going to give a talk on the jazz of physics, music, and the structure of the universe. It's going to be co-presented with the Center for Interdisciplinary Research in Music, Media, and Technology.